So first thing, who we are. We is Polytechnic Biomass Energy. It's a family business with headquarters in Austria. We've got an export rate of about 95%. We've got about 250 staff. We built our first boiler plant in 1965, so this year it's our 50-year anniversary. We've been installing every year about 150 to 200 megawatt of thermal energy, which equals roughly to about 30 to 50 boilers. That's what we do every year, which gives us a turnover of 70 to 80 million dollars a year just on wood boilers. And wood energy plants, we've done about 3,000 of those plants. We own and operate our own plants, so we are well aware of operating costs and what needs to be considered in owning and operating those plants. We've got our management systems. We've got offices and representations in over 20 countries worldwide, and as far as we know, we are the only European biomass boiler supplier with an established office in Australasia. What we do is wood-tailored wood waste and biomass combustion and gasification systems. I've got roughly about eight different combustion solutions, over 100 different furnace designs, so we haven't a standardized boiler range. All our systems are tailored for the application. We do boiler plants from 300 kilowatt up to 30 megawatts. Energy plants, most of them are the larger ones, are district heating plants up to 60 megawatt thermal. And we do power plants from 200 kilowatt electric up to 20 megawatt electric. We do cogeneration, tri-generation, emission control system, fuel handling system, so whatever you really need for an energy plant. One thing which we always highlight in our presentation, or I highlight in our presentation, is really the disadvantages of fossil fuels compared to the advantages of renewable energy. And if we look at the fossil fuels, the cost of fossil fuels are really significant. I mean, when I saw just recently from Statistic New Zealand, the only industry in New Zealand which at the moment grows is the fossil fuel industry by 12%, which is actually quite scary if at the same time Europeans and the rest of the world try to reduce the amount of fossil fuels. So the health-related cost, just the health-related cost due to air pollution worldwide is about 1.2 trillion US dollar. It kills about 5 million people worldwide. Water pollution or health-related cost, for example, in New Zealand, there's a report saying it's about $4.28 billion annually. Same as with financial crisis, oil shocks, wars, terrorism, that's all caused by securing fossil fuels and by the impact of global warming. The other thing is with fossil fuels, most of the fossil fuels is used in large power stations. Those power stations waste about 60% of their energy. If you would put that into wagons on a rail, you could fill about 15 million of those wagons. That would go about 20 times around the world. That's just the energy which we waste. They're not using that at all. I mentioned global warming, so rising sea levels, droughts, and even the impact then in New Zealand. The New Zealand drought, according to Minister Bill English, cost the New Zealand economy about $2 billion. So far I haven't seen anything what the government does to change that, to reduce the greenhouse gas emissions. The IMF says worldwide we subsidize fossil fuels by about $1.9 trillion. That's just how much we subsidize fossil fuels. I just thought I mentioned it. So the advantage really of renewable energy in today, talking about biomass or woody biomass, is really that it's a neutral carbon cycle. So if we basically take the plants, absorb the CO2 as they grow, they store it in the plant, and if we convert it into energy in a controlled environment, it releases basically the CO2 back. If we don't use the biomass, if we leave it in the forest, either we burn it off like we do it in New Zealand, or it catches fire at some stage anyway. But what it also does is during the decomposition process, it also releases lots of methane, which increases the greenhouse gas emission more. So using biomass in a controlled environment is actually a lower greenhouse gas emission than just let it rotten somewhere. Which type of biomass do we use in our boilers? From very high quality fuels, which would be dry fuels, fuels with high energy density like wood pellets, wood briquettes, or dry wood chips, down to the very low quality fuels, which could be any form of, I don't know, construction, demolition wood, peat, horse manure, chicken litter. Those are plants which we do as well, so that's the lower quality fuels. In New Zealand or in Europe, actually, those types of biomass are pretty much standardized in certain codes and standards. The main standard, which also the Bioenergy Association has used, is the EN 14961. There's a newer version. It's a 2010 version. It basically specifies the traded form, the size, the moisture content, the ash, the bulk density, the energy density, all what boiler suppliers or fuel suppliers need to know. One important thing to compare, especially biomass with coal boilers, is people or whoever decides on efficiency or comments on efficiency just should be aware that there are 4 heating or calorific values. We've got a gross calorific value on a dry basis, we've got a net calorific value on a dry basis, we've got a net calorific value on a dry basis, and we've got a net calorific value on a received basis. When coal boiler or gas boiler suppliers talk about efficiencies, they typically talk about the gross calorific value, whereas when wood boiler suppliers talk about efficiency, they talk about the net calorific value, which makes quite a big difference. In general, depending on the moisture content, on the ash content, the calorific value, of course, decreases of woody biomass. So the higher the moisture content, the lower the calorific value. We've got here a megajoules per kilogram from 5 to 19, and we've got here the fuel moisture content from dry to over 60%. If we consider that now as a boiler fuel, the first thing is what we look at is we look at certain constituents. So we look, for example, first of all, we look at the moisture, we look at how much ash is in the fuel, how much nitrogen is in the fuel, how much sulfur, how much chlorine, how much potassium is in the fuel, and then we look at a couple of other things like sodium and zinc and other constituents. So with those constituents, we very fast can say what's for us a very good fuel, what's a standard fuel, what's a low quality fuel, and what's really special fuel. And the impact on those is, of course, the higher the moisture content, the more sophisticated the boiler plant, the higher the ash content, the higher the problems you've got with wear, with cleaning, with power consumption, with ash disposal costs. On nitrogen oxide, that's quite a big topic in Europe, not so much in New Zealand so far. Sulfur on biomass, actually it's not really a big deal unless the sulfur content goes really higher. Then we have got the same challenges on a lignite boiler or on a coal boiler. And potassium is also quite an important one, like chlorine, which causes corrosion and which causes fouling and slagging and clankering. So that's some of the components we look at. So what's the disadvantage between having a high quality fuel or a low quality fuel? If I compare those, the advantage of having a high quality fuel is, of course, I can buy a cheaper boiler plant. I've got less contamination, hence less maintenance on the boiler plant. So it's a clear advantage of clean fuel. The disadvantage is it is an expensive fuel. The fuel cost, based on the experience of other markets, they will increase over time with the growing demand, and there's just a limited fuel availability. If I compare that now with cheap fuel almost has got an unlimited availability, so there's always some sort of waste stream, but it requires a much more expensive boiler plant, or a more expensive boiler plant depending how low the fuel quality is. It has got higher maintenance costs, and there are just less boiler suppliers which can offer you such a system, which is also a disadvantage. But there's, as I said, there's a lot of waste products. So for example, in New Zealand, I'll just show those pictures because the harvesting methods compared to Europe are quite different. So we basically just go into the forests and clear everything out, which causes erosion. And then we leave a huge amount of biomass in the forest. And the amount of biomass which we just leave in the forests or on those clearing sites is just huge. I mean, it's just here, for example, it's just the central North Island. What's left there is basically equals to 1.7 million barrels of oil that just rots there without any use, really. If I compare that, for example, to Austria, they harvest the timber quite different. They've got quite a big network of forest roads, and they take basically out just small stripes from the mountains. They've got then those landing sites, and on those landing sites, they basically use all the materials, so that goes to a sawmill, but all the other stuff, all this lash just gets hocked and chipped and shredded and then supplied to energy plants. Just looking at a couple of plants which we installed in New Zealand, showing what fuels they are using, and I will go into more detail a little bit later. So those are typically $4 to $7 a gigajoule fuel in the Christchurch area. So it's all sorts of hocked fuel. Here again, $4 to $7 a gigajoule fuel, $4 to $7 a gigajoule fuel. With a little bit higher quality, it comes closer to a wood chip. As soon as you then go to wood chips, the price almost doubles in the Christchurch area. And if you go to wood pellets, then it triples. So that's just to keep in mind that the higher the fuel quality, the more expensive. Most of our customers don't want to spend that much money, so they typically buy material which is less than $4 a gigajoule, and that's the material they're getting, and that's the material they're using. And especially the larger boiler plants, they run 100% on that sort of stuff, and that wouldn't require any further sizing. So as you can see it here in those images, that's what the boiler gets. I just want to touch a little bit, because it was presented before, on the difference between coal and wood when it comes to combustion to volatiles. I mean, one of the biggest differences is, of course, the higher carbon content and the lower amount of volatiles compared to biomass. So when I talk about coal, it's 30 to 40% of volatiles, with a carbon content of sometimes 80 to 85% on the dry basis. Here we've got, on biomass, we've got a carbon content of typically less than 50 or close to 50%, with volatiles sometimes more than 85%, which is quite important when it comes to the combustion of biomass. So when we combust wood, or whoever combusts wood, first need to dry whatever goes into the boiler plant. So if you've got 60% moisture content, it just means 60% of the stuff which goes into the boiler is just water, and that water needs to be evaporated, so that absorbs a huge amount of energy. Once you've basically evaporated most of the water, a gasification process, a pyrolysis process starts. In that gasification process, we basically just generate a syngas. So even in a boiler plant where we combust it on a grate or whatever the combustion system is, we first produce a gas which then gets combusted in that system. And it's important to understand that about 80% of the heat which we produce in that unit comes from the combusting of those gases. And just 20% of the heat comes from combusting the biomass on the grate. So it's all about gas combustion. And after, of course, everything is combusted, you're left with the ash. Just to give you an idea about when we talk about, for example, 85, 58 and 69% moisture content, what that actually does to the combustion system. So when we've got woody biomass, we've got ash, we've got char, we've got volatiles, we've got water. And if we oxidize, ideally we just get carbon dioxide and we get water. So in the first stage, as I explained before, we evaporate the water, then we do the gasification, then we do the char burning, and then basically we combust all the gases which we've generated. If I scale it down on bark now, saying, okay, that's a bark with 13% moisture, ash content, and 69% water, there's not much carbon left, which basically gives me the energy. So my calorific value is very low. And it gets even worse on sawdust, although there's much less ash, but my calorific value with similar moisture content drops to 4.2 gigajoule, which is almost impossible to combust. So back to that slide, what we need in our boiler plants, we need to have, at least to run it on low emissions, we would like to have 6 megajoules per kilogram or 6 gigajoules per ton. And then in different furnace systems or combustion systems, one are parallel flow or co-current, which are typically for dry fuels, and then the counter-current, which I will explain in a minute. So when we do energy plants, those is, they all look different, because as I explained before, they are tailored systems. That's for example a hot water boiler plant which just combusts grain. So in this case, it has got an additive dosing system, it has got a bakehouse, that's the combustion system, the fuel handling system, and the boiler. That's a thermal boiler plant, combustion system, boiler. I'll explain it later in more detail. That's a steam power plant, for high ash content fuels, and those are just hot gas generators. But what all those systems have got, they basically have got its own combustor. So before we go into the heat exchanger, before we transfer the heat onto the heat transfer media, we completely combust the gases. So those are those green boxes here, before we then finally go into the heat exchangers. So to explain what's happening in those combustors, I basically just take a cross-section of one of those plants. That's a, I don't know, 15, 16 megawatt boiler. Superheated steam but lower pressure. So we've got here our fuel storage area, we've got the feeding systems, that's the combustion system. And we've got here a combination of fire and water tube boiler, and then there are all sorts of other equipment here. So what I would like to show is a cross-section through that combustion system. So when we look at that combustion system, what it has got, in this case, it's a water-cooled step grate, so the combustion happens on the grate. We basically reciprocate the grates and transport the fuel as we move the grate. There are all sorts of air systems, secondary air, flue gas circulation, tertiary air system, which I explain shortly. When we take the cross-section through that system, it basically shows that's the area where we push in the fuel, and that's the grate here. That's a water-cooled step grate. So we push material onto that grate and have split that grate into 4 zones, because it's a larger plant. So we've got a drying zone, we've got a gasification zone, we've got a char burning, and the ash formation zone. Each of those zones are controlled independently. So we've got a level control, we've got its own primary air fan, its own flue gas circulation, and its own grate drive. So if you want it as a system which has got 4 independently controlled grates in one system. But what we do there, as I've explained here, we first need to dry it, then we need to gasify it, then we need to do the char burning, and then the ash formation. So actually what's required to efficiently combust biomass is what's happening in that boiler plant. Because that's a design for wet or higher moisture content fuels, there's a lot of focus on how do we evaporate the water, how do we dry the fuel. So first of all, here we use preheated air, so depending on how high the moisture content is, the combustion air has between 80 and 180 degrees Celsius, which helps, of course, to dry the fuel, because if your combustion air is 180 degrees hot, it dries the fuel pretty fast. What we also have got is it's a counterflow design, so you basically push the material from one side, and the hot gases which we produce here go over that fuel bed and support the drying process. Another thing which we've got in the system, it's an inclined arch which radiates the heat back, and it narrows down to the end of the grate. So that just means here basically we dry it with air, here we dry it with the flame, and here more and more the arch. So that just helps us to utilize up to 60% moisture content fuels in those boilers and still maintaining very low emissions. What we've then got is that we're not getting too hot in that zone, and there's a flue gas circulation, so we take the gases from the back, we put it back into the system and control the furnace temperatures here, typically to around measured temperatures of about 550 to 750 degrees, whereas as soon as we add then further oxygen in the upper section of that unit, we increase it to 750 to 950 degrees typically. And that's when we then completely combust the gases. What we also do is that system de-ashes it automatically via the grate, but it also de-ashes the furnace via that second part here, so that we get very little particulate emissions to the downstream heat exchangers. If we now look at most of our systems, or challenging systems, are modeled, so we look basically at the velocities of the system, we look at the oxygen content, at the carbon monoxide concentration, the gas temperature. I explained it on a more sophisticated model a little bit later. Different to what I've explained before, that's for example a co-current or parallel flow design, especially for dry fuels, where there's no need to dry as much. So sometimes we don't even do air preheaters on those systems. So we combust basically closer to the infeed area, the grates are shorter, and the energy basically, or the gas, leaves the system as fast as we can, because it's actually quite a high heat release in these parts of the systems. Those furnaces are typically also smaller than the furnaces for the wet fuel. But here again, that's a thermal boiler where we have got the combustion system here, refractory line duct, the boiler, all those systems are modeled. And what we model, I explained it here in a more sophisticated plant. That's actually a plant which we've designed for superheated steam. That's a power plant, 12 megawatt boiler, 3 megawatt electric. And in Europe, they just shut down those boiler plants for 1 or 2 weeks a year, so they expect you to run that boiler plant for 50, 51 weeks a year. But the problem which we had here, the fuel was compost rejects, 20% ash content and 60% moisture content. So we had to come up with a design which is quite sophisticated to handle high moisture and high ash content fuels. So we've got here a grate, we've got here the combustion part, the radiation part of the boiler before we finally go into the superheaters. That's the grate, so we still stick to our 4 zones in this system, but the gases here have got much more residence time to oxidize and to complete the combustion, between 3.4 and 6 seconds. When I talked about volatiles before, of course with the volatiles we produce a certain amount of gas, and to cool that we also use our flue gas recirculation system. We add all sorts of air to the system, and all those air streams are basically modeled, which give us basically the velocities in the system. And on high ash content fuels, we then also want to understand where does the ash hit hot furnace walls. So we look at the ash impingement areas and rates and get a good understanding where the zones are, which could be a little bit critical. Same is with the oxygen concentration. Close to the grate, we run with very low oxygen, so that's almost like a gasifier, whereas in the, as soon as we add then more air, it's basically a combustion zone. So if you want this, that's a gasifier, and that's almost like a gas burner. What we then do is we model the furnace wall temperatures, flue gas temperatures, and with the flue gas temperature, especially on power plants or superheated steam power plants in combination with biomass, it's important to understand high temperature chlorine corrosion. So what we do with the systems, we don't want to get too hot on the biomass combustion system, so we combust with lower temperatures close to the grate. We increase the temperature to about 900, 950 degrees to complete the combustion, to oxidize everything. But before we enter the superheater, we take the energy back out of the system via membrane walls. What that does is just drops basically the stresses or the corrosion risk for the superheater, and the lifetime of the plant is much longer. Not to mention that we achieve with those designs very low carbon monoxide emissions. So 15 is basically guaranteed value, but I haven't seen any plants where we monitor carbon monoxide which are above 10 milligrams. So most of our boiler plants are between 3 and 5, which is basically completely combusted. And the particular emissions are also quite low. So efficient wood and biomass combustion needs to happen, to our opinion, in 4 stages, because you need to dry it, you need to gasify it, you need to do the combustion, and you need to do the de-ashing. The temperatures in the close to where the combustion happens should be below 800 degrees. Where you do the gas combustion, it should be above 800 degrees ideally, because then it completes the combustion. Sophisticated systems have got all sorts of air staging systems. That's from primary air system, secondary air system, flue gas recirculation system, tertiary air systems, there are all sorts of systems. Once you get a proper staging, NOx emissions are also very low. Turbulence, when you mix air with gases, you would like to have turbulences, so there are zones with turbulences. You would like to have a gas residence time to give the gas enough time to oxidize. In the combustion, you don't want to give the system too much oxygen, because otherwise it's an inefficient system. So close to the combustion zone, you run with low lambda or low oxygen excess. In the gas combustion zones, typically between 1.2 and 1.6. Combustion system adiabatic condition, so you don't want to extract a lot of heat, because that would be counterproductive, especially if you're aiming for higher temperatures. And you also need to design it for a proper heat load. That's one of the combustion systems, for example, just to show you around the combustion system what sorts of instrumentation and fans we've got on the more basic systems. There are nowadays much more sophisticated systems, which I don't think we've got the time to present today, but control systems wise. But in this case, you see here the primary air fans, all on variable speed drives. You've got all sorts of control dampers and shut-off dampers. Same is with flue gas recirculation systems here. Secondary air system, so it's a well-controlled combustion process, really. And what you get is basically just clean combustion. How the combustion looks on the grate, it's something like this. So you see really the last stages of the gasifying and char combustion. If you could look just half a meter beyond it to the back, you would see it's still drying and gasifying. But that's a boiler which runs at 100% load. So that's not something which just idles, it runs at 100% load. What you then get in the upper parts, that's basically just looking through one of the side classes. all you've got there is a hot glowing mass of refractor which sits at 950 degrees and just oxidizes the gases. What you also get with biomass is all sorts of contamination, so it's a little bit difficult to see, but it's rocks and stones of that size which sometimes come with the biomass. And ideally, it's not good to feed the boiler with that stuff, of course, because it doesn't add any value. But it shouldn't stop the boiler plant. So we know at times get operating conditions where really lots of that type of contamination goes into the boiler plant. What you get is the ash from the grate is typically tramp metal, stones, rocks, a little bit of clinker. That's typically your ash from the boiler. What you get is from the heat exchangers or emission control system is lightish grey ash, which just indicates it's completely combusted. So the amount of unburnt carbon in the ash typically sits below 5%. That's also a legal requirement in Europe. So that's why you hardly could run any New Zealand boiler in Europe, because it just wouldn't meet the unburnt carbon requirements. So to have an efficient wood and biomass combustion system, you want to have low carbon monoxide, you want to have low excess oxygen, flue gas circulation, which controls the temperatures. Combustion air temperatures should be high. Moisture content of the fuel, the lower the moisture content of the fuel, the higher the efficiency. That's even with advanced system. Flue gas temperature, back-end temperatures. Most of our plants which we run in New Zealand typically would have back-end temperatures of, I don't know, 115 to 140 degrees Celsius, actually quite cold at the back-end. You want to minimize radiation losses and, of course, your unburnt carbon. Talking about investment cost versus running cost. One important thing to understand here is really how do you utilize your plant? What's the utilization of your plant? Do you provide the energy to a continuous drying kiln or to an industrial process? Do you use this for glass houses? Do you use it for district heating? Do you use it for schools? When it comes to utilization, schools are probably the worst ones because they don't need the heat a lot. Whereas if you go for drying kilns or likes of Fonterra, they've got actually quite a high utilization. What I did here, first an example on a 1 megawatt boiler and then later I think on a 10 megawatt boiler, is basically just looked at the different systems which can handle different fuels. So the higher the quality of the fuel, I said that before, the higher the quality of the fuel, the more basic and the more, cheaper the energy plant. That comes from the fuel storage requirement, that comes from the feeding requirement, from the combustion system, everything. So we've got, for example, here 1 megawatt boiler plant. If we supply that mechanical and electrical stuff, it's probably a $115,000 exercise. If we go for a system which handles just wood chips, it's probably about a $300,000 exercise. And if we go for the more sophisticated systems, it's a $450,000 exercise. So there's quite a big investment difference between a 450 and 150. So if you go to a customer and say, okay, he needs a 1 megawatt boiler plant, and say, yeah, our boiler plant costs 450, and someone else gives him a price for 150, he probably doesn't continue to talk to you. But it's important to understand that those systems are designed for low quality fuels, and these systems are designed for high quality fuels. And I put a number just to those fuels, $6.50 for the low quality, $11 for the medium quality, and $14.50 for the high quality fuel. And if you utilize your plant in this example just for 25%, so that just means 25% of the time you use the boiler plant with 80% load, it gives you a utilization of about 20% of that heat plant. It definitely matters how much the plant costs. So with these type of utilizations, you're rather better off in spending less money and spending more money on the fuel. But as soon as you increase the heat plant utilization, that starts to change now. So if I say, okay, I use the boiler 40% of my time, the difference of the return on investment of the additional costs drop back to the order of about 3 years. If I start to use the boiler as much as I should use a wood boiler, then the cost of the wood boiler is completely irrelevant. All what matters is how expensive is your fuel. And if you do that on a, for example, on a 10 megawatt boiler plant, and someone can give you that boiler for free, gives you a 10 megawatt boiler for free. If that boiler can't handle low quality material, you will spend about $40 million just on additional fuel costs, and that's really important to understand. So it's not so much about the energy plant, it's more about the fuel. I was once challenged, it was probably about a year ago, by one customer which said, I think we offered them a 4 megawatt boiler plant for $2.5 million, and he said, I can do it for $1 million. I just said, no, you can't. He said, yes, I can. I said, no, you can't. After I was back in my office, I started thinking, and actually it was a little bit premature to say that, because you can. Looking at those two heat plants, that's a hot water boiler, and that's a hot water boiler. Obviously, that's a little bit cheaper than this one. So I looked at certain areas where can you save money and what makes the price difference. And you find the main areas in the combustion system, so emissions, efficiency. You find it in the fuel handling system. You don't find it so much in the boiler because you still need a certain amount of heat exchanging surfaces. So that basically stays the same. That boiler, the more sophisticated one, would have an automatic cleaning system, whereas the less sophisticated one has got manual cleaning. So there's not much to gain in that area. There's lots of things to gain in health and safety, energy efficiency, transport cost. The more sophisticated the plant, the more gear you transport to site. The same as with the installation, cabling, piping. So, for example, just to give you an idea of cabling, we're supplying now 3 boilers to Burwood Hospital in Christchurch. A 2 megawatt wood boiler, a 4 megawatt wood boiler, and a 4 megawatt diesel boiler. The amount of cables we use is a steam boiler plant, quite a sophisticated one with all sorts of heat exchangers. It's about 30 kilometers of cable just in that energy plant. So the cabling cost, depending on the technology, can be quite high. Just to give you a couple of examples. When we talk about fuel handling system, that's a fuel handling system. It's probably, I don't know, we would do that, I don't know, for $30,000, $40,000 probably. That's a fuel handling system as well. We probably would do that for $3 or $4 million. So it's really important to understand what the customer needs. Same is here, for example, fuel feed system. So you've got here a fuel feed system. That boiler is just black area because it's quite high, but then they put a plastic barrel and all sorts of things, so that's not safe at all. Whereas a sophisticated system would have fire damper, sprinkler systems, and all sorts of fire protective devices. Or furnace sizes. Here, for example, they are all 4 megawatt boilers. That's a 4 megawatt furnace, that's a 4 megawatt furnace, and that's a 4 megawatt furnace. So that definitely has got an impact on the efficiency. Same is with the cleaning system. Those boilers have got automatic cleaning systems, those have got manual cleaning. De-aging systems. You can have systems where basically de-age in large containers or in silos, or you just open the boiler twice or 3 times a day. And I'm not sure how that's handled in New Zealand with health and safety, opening a door which is as a fire may blow back. But those are photos from or images from New Zealand installations. Or here, plant access. You can have access to all sorts of areas, or you basically got just one ladder, and yeah, at some stage you might need to get up there as well. Same as with heat insulation. The furnaces here, for example, they are air-cooled. All the radiation heat is used for the combustion here, so the furnaces, if you touch them, they're actually cold. Whereas that's a furnace, for example, very hot. So I'm not sure when we start to talk about hot or very hot, but that was very hot. So that was about 250 to 300 degrees on the outside. And that furnace needs to be de-aged manually once or twice a day. Talking about emission control, I think most of us are aware that in New Zealand we've got actually, although it's a green country, I always said it's a clean and green country. Living in the Hawke's-Bay, I wouldn't say so much it's as clean as I thought it is, and we definitely have got some air pollution issues. I said before, air pollution in New Zealand, not only that it kills people, it costs a lot of money, and its main problem in the industrial heat, to my opinion, is inefficient boiler plants. And the main reason for that is it's just a lack of air emission standards. So boiler suppliers in New Zealand basically supply what you ask them to supply. If there's no one who asks them for low emissions, they're not going to give you a better boiler plant. That's just how it is. But those emissions have quite a big impact on your health, and depending on what it is, I mean, open burning, of course, is also a very bad thing, which is banned in Europe, so you just can't burn all your rubbish in the backyard. Or when I say rubbish, I'm talking about wood waste. And inefficient boilers also contribute to those. Not surprisingly, although I don't know exactly the split, but not surprisingly is asthma, for example, 2 to 3 times as high as in Europe. but part of that might be also caused by the cold and damp houses. So it's a little bit difficult to see or to understand how much it's actually caused by the air pollution. But there's a report which you can look up on the internet. It basically just comes up with all the numbers, why people die prematurely and what the air pollution problems are. And if you look at the World Health Organization limit, there's a World Health Organization limit of 50 micrograms, and you would find that a lot of areas in New Zealand, especially in winter, exceed those emission limits quite significantly. It's getting better. So that's, for example, one photo from Dunedin. As far as I know, they installed now a gas boiler, so that's basically solved. It gets better in Christchurch, it gets better in other areas, but at the time when I got those numbers, it was still as bad as that, but it's getting better. Not surprisingly, the guys with the lowest emissions, I'm not sure if I've got Ingvar Cargill here, but I wouldn't be surprised if it's as low as in Wellington. If you've got high wind, I've got low emissions. But what we also did with our energy plants is I was contacted by a couple of guys of a village in Germany in 1999, and they said, okay, we've got an air pollution problem, what can we do about that? And they had, I don't know, 400 or 500 houses with all sorts of wood burners, and we said, there's not much you can do there. The only thing you can do is you install a district heating plant, and we provide the energy from the district heating plant, install an efficient wood boiler plant. They liked the idea. It took them 2 years basically to convince the first 80 or 100 people to sign up. Once they've signed up, they started to build a district heating plant. And what you can see here is over 10 years, as more and more houses connected to the district heating plant, you completely clean up your airshed. It's probably also useful to understand that all the different woody biomass sources, they all have got different constituents. Because they've got different constituents, they've got different particulate forming mechanisms. So it's different on wood chips, on bark, and on construction and demolition wood. But most of those emissions, people started to talk about PM10, then started to talk about PM 2.5. Now in Europe they talk about PM1. On wood and biomass boilers, there are two fractions. The one is which can be easily separated with multicyclone. That's a fraction here between 10 and 100 micrograms. And then there's another fraction below 1 microgram. So it doesn't matter if we talk about PM10, PM2.5, or PM1. It's actually all the same, because the emissions, you will have all those emissions below PM1 anyway. And then there are all sorts of emission control systems, electrostatic precipitators, bakehouses. They basically do all the same. They reduce particulates. They don't reduce anything else apart from a bakehouse. Once you start to install bakehouses, you can add additives, and those additives target other substances. So you can add, I don't know, hydrated lime or activated carbon, and all sorts of products which target certain substances. The bad thing with a bakehouse is it requires good combustion quality on the one hand, because otherwise it catches fire. That's one problem. And it depends also on your guaranteed emission limit. If you use a bakehouse for 50 milligrams, it's more expensive to run than electrostatic precipitator. If you talk about 5 or 10 milligrams, it's actually quite a competitive. And it also requires a steady load on the boiler, so you wouldn't want to have a bakehouse on a boiler which you start twice a week. That's something which basically has an impact on the lifetime of the bakes and actually makes the system even more expensive. I know we don't talk about NOx emissions, but when we designed our boiler plants about 20-25 years ago, we were targeting carbon monoxide, and I don't know, 5 years later we targeted particulate emissions, then we targeted NOx emissions, and now we target again particulate emissions, especially the PM1s. But in general, the higher the nitrogen content of your fuel, the higher the NOx emissions. I think that was talked about in the morning. There are all sorts of heat recovery technologies. On economizers, basically the lower your back-end temperature, the higher the efficiency of your plant. The only thing to consider here is the acid dew point of the gases. So you don't want to cool them down too fast, because otherwise you get corrosion. That's probably the most important thing to consider on economizers. If you then start to use the latent heat, or the heat which is basically stored in the water vapor, the amount of energy which you can recover is huge, but it depends really on who can take that low-grade energy and what's your moisture content. So the higher the moisture content of your fuel and the lower your back-end gas temperatures, I mean, we installed system, they've recovered 30% of the installed boiler capacity, but just because they could use 20-25 degree cold water. So there are all sorts of systems, scrubbing systems. We built a couple of those scrubbing systems. All they do is they just quench the gases, basically transfer the energy onto the water. Problem with those systems in Europe is they are not allowed anymore because, or you start to struggle because they shift the problem just into the water. So all your emissions are basically not in the air, they are now in the water, and Europeans are very fussy about their water quality. Hence, there are other systems. So you would normally install a bakehouse electricity precipitator before you then install all sorts of heat exchangers. Those are combinations of economizers and condensing heat exchangers. Those are systems which basically just condense the gases and preheat air, combinations of heat exchangers in the air. There are all sorts of heat recovery systems. And it always depends on the fuel price. To my opinion, at the moment, the fuel price in New Zealand is so cheap that it's worthwhile to use those systems, whereas in Europe the fuel at times is more expensive. Fuel handling systems, how do we handle it? From very basic systems and cheap systems which you use on small boiler plants, which basically just got a hopper where you dump the material, and there are all sorts of mechanisms which feed it into your boiler plant. To the more sophisticated one, industrial plants, where you basically have got bunker systems, a front-end loader, where they dump it into live floors. And it's typically installations which you would find on our plants, is where customers have got all sorts of material, and all they do is they take a front-end loader, take a bucket load of this, a bucket load of that, and feed the boiler plant. And even on the more sophisticated one, district heating plants, or that's a power plant, at times when you go there, they just got bark, because they got the bark cheap, and on other days they just got wood chips. And it's really, that gives them a bit of a buying power. The fuel storage systems, you've got here the could be quite basic bunker, but could be also sophisticated areas. Or that's, for example, for a hospital where you don't use a front-end loader. All they do is they've got trucks, they're just pushing back, and have then got a walking floor in there, and basically just dump the material onto that live floor. But there are all sorts of systems. There could be auger-fed systems and silo systems, and even silos where we've got the boiler sitting underneath them. And it's on fuel handling systems, there are many things which we can do. Most of the systems which we use would have a hydraulic ram, so we basically just push the material onto a trough, and that trough basically feeds the boiler. So if you can see here, that's the live floor, that's the feeder, and that feeder basically feeds that boiler with the biomass. And you can see here, there's hardly anything which can block it, so they're quite large openings, and those openings are just responsible that you can use material up, I don't know, 500, 600, 700 millimeter. That's not a problem, even on 300 kilowatt boilers. Sorry, they also have got a cutting device, so if something is oversized, it basically just cuts it off. But here again, I mean, you can do, I mean, those are the larger plants. They've got all sorts of fuel storage areas, all sorts of live floors and conveying systems, or drainage systems. I mean, what we do is we do once a year normally, we call it a showcase tour, where we go to 10 or 12 plants in Europe with Australian and New Zealand customers. We did that the last 3 years, and this year we will do it again in October. We don't promote it as such, but people who know that we do that are quite keen to go there. And that was from the last October visit, where we had a couple of guys from, in this case, from Chile, New Zealand, and Australia. And that was one power station, for example, where they dump the material just into a large bunker. The crane takes it out there, just stores it wherever it needs to store it, so it works with a certain software. It knows where it stores what sort of material, and then feeds the day bunker.